List of deep learning algorithms. Deep learning algorithms form the backbone of many state-of-the-art machine learning applications, enabling the development of complex models capable of learning and making predictions from vast amounts of data. In this explanation, I will provide a list of prominent deep learning algorithms. 1. Feed-forward neural networks, FNNs. Feed-forward neural networks, also known as multi-layer perceptrons, MLPs, are the foundation of deep learning. They consist of an input layer, one or more hidden layers, and an output layer. FNNs propagate data in a forward direction, with each layer's neurons applying a nonlinear activation function to their inputs. Backpropagation is commonly used to train FNNs by adjusting the weights based on the calculated error. 2. Convolutional Neural Networks, CNNs. CNNs excel in analyzing grid-like data such as images, audio spectrograms, or time series. They leverage the concept of convolution by applying filters to local receptive fields, capturing spatial hierarchies in the input. CNNs often include convolutional, pooling, and fully connected layers. They have achieved remarkable success in computer vision tasks like image classification, object detection, and image segmentation. 3. Recurrent Neural Networks, RNNs. RNNs are designed to handle sequential and temporal data, making them suitable for tasks such as speech recognition, machine translation, and sentiment analysis. They introduce recurrent connections, allowing information to persist throughout the sequence. The most common variant, the long short-term memory, LSTM, network, addresses the vanishing gradient problem and effectively retains long-term dependencies. 4. Generative Adversarial Networks, GANs. GANs consist of two competing neural networks, a generator and a discriminator. The generator network learns to synthesize new data samples, while the discriminator network learns to distinguish between real and generated samples. Through an adversarial training process, GANs can generate realistic data, such as images, audio, or text, with applications in image synthesis, data augmentation, and anomaly detection. 5. Autoencoders. Autoencoders are unsupervised learning models used for dimensionality reduction, data compression, and anomaly detection. They consist of an encoder and a decoder, where the encoder compresses the input data into a lower dimensional representation, and the decoder reconstructs the original data from the compressed representation. Variants such as variational autoencoders, VAEs, introduce probabilistic modeling and allow for the generation of new data samples. 6. Reinforcement learning, RL. RL is a paradigm where agents learn optimal actions through interactions with an environment. Deep reinforcement learning, DRL, combines RL with deep neural networks to handle high-dimensional state spaces. Algorithms like deep Q networks, DQNs, and proximal policy optimization, PPO, have achieved remarkable success in domains such as game playing, e.g., AlphaGo, and robotics. 7. Transformer networks. Transformers are a revolutionary architecture introduced by the "attention is all you need" paper. They excel in sequence-to-sequence tasks, such as machine translation and text generation. Transformers rely on self-attention mechanisms to capture dependencies between different positions within the input sequence, eliminating the need for recurrent connections. 8. Graph Neural Networks, GNNs. GNNs are designed to process graph-structured data, representing relationships between entities. They operate on node and edge features, capturing both local and global information. GNNs have been successfully applied in social network analysis, molecular chemistry, and recommendation systems. 9. Deep reinforcement learning for robotics, RLR. RLR algorithms combine deep learning with reinforcement learning to train robots to perform complex tasks. These algorithms enable robots to learn manipulation skills, locomotion, and navigation in real-world environments. Methods within RLR include deep deterministic policy gradient, DDPG, trust region policy optimization, TRPO, and proximal policy optimization, PPO. 10. Deep belief networks, DBNs. DBNs are generative models that consist of multiple layers of restricted Boltzmann machines, RBMs. RBMs are trained in an unsupervised manner to learn the underlying probability distribution of the input data. DBNs can be used for tasks like dimensionality reduction, feature learning, and generative modeling. 11. Capsule networks. Capsule networks, also known as CAPS nets, are an alternative to traditional convolutional neural networks. They aim to overcome the limitations of CNNs in capturing spatial relationships. Capsules represent instantiation parameters of specific entities and use dynamic routing to learn hierarchical relationships between entities in the input. 12. Deep residual networks, ResNet. ResNet introduced the concept of residual learning, addressing the problem of vanishing gradients in very deep networks. Residual connections allow the network to learn residual mappings, enabling the training of deeper architectures with improved accuracy and ease of optimization. 13. Adversarial autoencoders, AAEs. AAEs combine elements of autoencoders and GANs to generate realistic data samples. They use a variational autoencoder framework with a GAN-like adversarial training process to learn a latent representation of the input data. AAEs are capable of generating diverse samples and have applications in image synthesis, data augmentation, and unsupervised representation learning. 14. Deep reinforcement learning from human demonstrations, DRLHD. DRLHD algorithms combine reinforcement learning with human demonstrations to accelerate and improve the learning process. By leveraging human expertise, these algorithms can learn complex tasks more efficiently. Methods like hindsight experience replay, HER, and Dagger, dataset aggregation, fall into this category. 15. Deep metric learning. Deep metric learning focuses on learning similarity or distance metrics between data samples. By training deep neural networks to embed data points into a space where similar samples are closer together, it enables applications such as face recognition, person re-identification, and image retrieval. 16. Deep generative models. Deep generative models aim to capture the underlying distribution of the data and generate new samples that follow the same distribution. Variational autoencoders, VAEs, and Generative Adversarial Networks, GANs, are popular deep generative models capable of synthesizing realistic and novel data samples. 17. Deep reinforcement learning with memory. Memory-augmented deep reinforcement learning algorithms integrate external memory structures, such as neural Turing machines or differentiable neural computers, with deep reinforcement learning. These models enhance the agent's ability to retain and utilize information over extended sequences or episodes, leading to improved performance in complex environments. This list provides a glimpse into the diverse landscape of deep learning algorithms. Each algorithm has unique characteristics and is suited for specific problem domains and data types. Deep learning continues to advance rapidly, with ongoing research and the emergence of new algorithms, further expanding the capabilities of this field and its applications. Thanks for watching.